LAMP instrument sheds light on lunar water movement using the Southwest Research Institute-led Lyman Alpha Mapping Project (LAMP) aboard NASA's Lunar Reconnaissance Orbiter (LRO). Scientists have observed water molecules moving around the dayside of the Moon. A paper published in Geophysical Research Letters describes how LAMP measurements of the sparse layer of molecules temporarily stuck to the surface helped characterize lunar hydration changes over the course of a day. Up until the last decade or so, scientists thought the Moon was arid, with any water existing mainly as pockets of ice in permanently shaded craters near the poles. More recently, scientists have identified surface water in sparse populations of molecules bound to the lunar soil, or regolith. The amount and locations vary based on the time of day. This water is more common at higher latitudes and tends to hop around as the surface heats up. This is an important new result about lunar water, a hot topic as our nation's space program returns to a focus on lunar exploration, said SRI's Dr. Kurt Rutherford, the principal investigator of the LRO LAMP instrument. We recently converted the LAMP's light collection mode to measure reflected signals on the lunar dayside with more precision, allowing us to track more accurately where the water is and how much is present. Water molecules remain tightly bound to the regolith until surface temperatures peak near lunar noon. Then, molecules thermally desorb and can bounce to a nearby location that is cold enough for the molecule to stick or populate the Moon's extremely tenuous atmosphere, or exosphere, until temperatures drop and the molecules return to the surface. SRI's Dr. Michael Poston, now a research scientist on the LAMP team, had previously conducted extensive experiments with water and lunar samples collected by the Apollo missions. This research revealed the amount of energy needed to remove water molecules from lunar materials, helping scientists understand how water is bound to surface materials. Lunar hydration is tricky to measure from orbit due to the complex way that light reflects off of the lunar surface, Poston said. Previous research reported quantities of hopping water molecules that were too large to explain with known physical processes. I'm excited about these latest results because the amount of water interpreted here is consistent with what lab measurements indicate is possible. More work is needed to fully account for the complexities of the lunar surface, but the present results show that work is definitely worth doing. Scientists have hypothesized that hydrogen ions in the solar wind may be the source of most of the Moon's surface water. With that in mind, when the Moon passes behind the Earth and is shielded from the solar wind, the water spigot should essentially turn off. However, the water observed by LAMP does not decrease when the Moon is shielded by the Earth and the region influenced by its magnetic field, suggesting water builds up over time, rather than raining down directly from the solar wind. These results aid in understanding the lunar water cycle and will ultimately help us learn about accessibility of water that can be used by humans in future missions to the Moon, said Amanda Hendricks, a senior scientist at the Planetary Science Institute and lead author of the paper. A source of water on the Moon could help make future crewed missions more sustainable and affordable. Lunar water can potentially be used by humans to make fuel or to use for radiation shielding or thermal management, if these materials do not need to be launched from Earth. That makes these future missions more affordable. The funding for this research came from NASA Goddard Space Flight Center's LRO Program Office, including an LRO LAMP subcontract between SWRI and SCI, and the team received additional support from a NASA Solar System Exploration Research Virtual Institute (SSERVI) cooperative agreement. Ingredients for water could be made on surface of Moon, a chemical factory when a stream of charged particles known as the solar wind careens onto the Moon's surface at 450 km per second or nearly 1 million miles per hour. They enrich the Moon's surface in ingredients that could make water, NASA scientists have found. Using a computer program, scientists simulated the chemistry that unfolds when the solar wind pelts the Moon's surface. As the Sun streams protons to the Moon, they found those particles interact with electrons in the lunar surface, making hydrogen H atoms. These atoms then migrate through the surface and latch onto the abundant oxygen O atoms bound in the silica, silicon oxide, and other oxygen-bearing molecules that make up the lunar soil, or regolith. Together, hydrogen and oxygen make the molecule hydroxyl O, a component of water, or H2O. "We think of water as this special, magical compound," said William M. Farrell, a plasma physicist at NASA's Goddard Space Flight Center in Greenbelt, Maryland, who helped develop the simulation. "But here's what's amazing, every rock has the potential to make water, especially after being irradiated by the solar wind." Understanding how much water, or its chemical components, is available on the Moon is critical to NASA's goal of sending humans to establish a permanent presence there, said Orenthal James Tucker, a physicist at Goddard who spearheaded the simulation research. "We're trying to learn about the dynamics of transport of valuable resources like hydrogen around the lunar surface and throughout its exosphere, or very thin atmosphere, so we can know where to go to harvest those resources," said Tucker, who recently described the simulation results in the journal JGR Planets. Several spacecraft used infrared instruments that measure light emitted from the Moon to identify the chemistry of its surface. These include NASA's Deep Impact spacecraft, which had numerous close encounters with the Earth-Moon system en route to Comet 103P, Hartley 2, NASA's Cassini spacecraft, which passed the Moon on its way to Saturn, and India's Chandrayaan-1, which orbited the Moon a decade ago. All found evidence of water or its components, hydrogen or hydroxyl. But how these atoms and compounds form on the Moon is still an open question. It's possible that meteor impacts initiate the necessary chemical reactions, but many scientists believe that the solar wind is the primary driver. Tucker's simulation, which traces the life cycle of hydrogen atoms on the Moon, supports the solar wind idea. From previous research, we know how much hydrogen is coming in from the solar wind, we also know how much is in the Moon's very thin atmosphere, and we have measurements of hydroxyl in the surface, Tucker said. "What we've done now is figure out how these three inventories of hydrogen are physically intertwined." Showing how hydrogen atoms behave on the Moon helped resolve why spacecraft have found fluctuations in the amount of hydrogen in different regions of the Moon. Less hydrogen accumulates in warmer regions, like the Moon's equator, because hydrogen atoms deposited there get energized by the Sun and quickly outgas from the surface into the exosphere, the team concluded. Conversely, more hydrogen appears to accumulate in the colder surface near the poles because there's less sun radiation and the outgassing is slowed. Overall, Tucker's simulation shows that as solar wind continually blasts the Moon's surface, it breaks the bonds among atoms of silicon, iron and oxygen that make up the majority of the Moon's soil. This leaves oxygen atoms with unsatisfied bonds. As hydrogen atoms flow through the Moon's surface, they get temporarily trapped with the unhinged oxygen longer in cold regions than in warm. They float from O to O before finally diffusing into the Moon's atmosphere, and, ultimately, into space. "The whole process is like a chemical factory," Farrell said. A key ramification of the result, Farrell said, is that every exposed body of silica in space, from the Moon down to a small dust grain, has the potential to create hydroxyl and thus become a chemical factory for water.